Yeah, the title of my talk, hopefully everyone can see this. The title of my talk is the Search for Alternative Supplementary Cementing Materials. And Rachel said, I'm a professor of civil engineering at the University of New Brunswick in Canada. And it's a delight to be able to attend this concrete conference. I only wish it wasn't virtual, as I always enjoy visiting Minnesota. Anyway, let's start off with a sort of very brief history, if you like, the history of calcareous cements, which goes back to 12,000 BC with the first use of calcareous materials as cementitious materials. Pozzolans didn't appear till quite a bit later. Pozzolans appeared about 2.5 millennia ago. And contrary to popular opinion, they didn't first appear in Italy in structures like the Colosseum. They appeared in ancient Greece, and the island of Rhodes is where we find our first example of the use of lime and volcanic ash. I'll also talk very briefly about the development of hydraulic cements, because this was an important step also in the history of the development of supplementary cementing materials. So yeah, we go back, as I say, 2.5 millennia to the first documented proven use of pozzolanic materials. This was a volcanic ash from the island of Thera in Greek. It's one of the Greek islands, also known as Santorini. And the volcanic ash is also known as Santorin earth. That's the name that's often given to the pozzolan. And this was used together with burnt limestone to produce concrete. Of course, we're more used to, we think of pozzolans as being developed in the Roman era. And the Romans did widely develop the use of pozzolanic materials. Roman mortar, which is a combination of volcanic ash and lime, was used in a number of structures, including perhaps amongst the most famous, the Colosseum, where it was used to cement the stone and marble facing together. But there's also dense pozzolanic concrete in the foundations and some of the arches and vaults of this building as well. Perhaps one of the most famous buildings for the use of pozzolanic materials is the Pantheon in Rome, which is almost 2,000 years old. This actually contains the dome of this structure is in fact cast in place concrete. The bulk of the structure, the curved walls, are masonry, but the dome is actually lightweight concrete, 2,000-year-old lightweight concrete. The lightweight was provided by a lightweight pumice aggregate, and holding all this together was a lime pozzolan binder, pozzolan being volcanic ash from Mount Vesuvius. The structure is still standing today. It's still in absolutely excellent condition, and it really is a testament to the use of pozzolans in producing durable concrete. Incidentally, the term pozzolan actually comes from the Italian town of Pozzoli, which was one of the best sources of volcanic ash for use by engineers. So from here, we're going to skip forward 1,600 years, because not really much happened in the life of pozzolans for 1,600 years. Well, of course, a lot happened. There's the fall of the Roman Empire, with the Dark Ages, the Renaissance, and Columbus's discovery of America. But during that 1,600-year period, pozzolans were still mainly used for lime. And then in the 18th and 19th century, we saw the development of hydraulic cements over a probably 150-year period, starting with the work of John Smeaton, developing a hydraulic cement for use in the Eddystone Lighthouse. The structure is still standing today, but not actually out at sea. It was brought back inland. It served its purpose for 100 years and is now a tourist attraction on the mainland. Following Smeaton's work, there's been various contributions towards the development of hydraulic cement, including the work of Louis Vicat. and of course canvas white in the US with his natural cement, Rosendale cement. Aspen is usually credited with inventing Portland cement. I'd say that Aspen really was the first person to actually patent Portland cement and patent the name, whereas all of these people really contributed to the actual development of what eventually became Portland cement. Portland cement was produced in the Copley mills as early as 1875, and by the time that the 19th century was over, Portland cement had really emerged as the most widely used hydraulic cement, and still is today. But we really have to acknowledge the contribution of some of these other people towards the development of hydraulic cement. So in the early 20th century, we start to see the use of pozzolans with Portland cement. And that's really what we've seen over the last 120 years, is pozzolans being used with Portland cement rather than being used for lime. And some early uses, I'm showing some photographs here of some early uses with in North America, in the US, in fact, all of these structures there. Pozzolans were widely used wherever they were available. A lot of these were raw pozzolans, such as volcanic ash and pumice, but some were calcined pozzolans, calcined shells, calcined clays, which includes metakaolin. So using a wide variety of structures. Pozzolans were very popular with the U.S. Bureau of Reclamation in the construction of massive concrete dams. The incentives for using pozzolans, of course, one is cost. It's cheaper than Portland cement. A lot of its construction was done during and between the wars, where cement was a shortage anyway. But also, of course, one of the incentives for using pozzolans, massive concrete construction, is that they allow control of the heat of hydration. So a great many structures were built during the first 50 or 60 years of the 20th century, using a wide variety of pozzolans. I'm just showing this one individual structure here, as I just love the glory hole in this. This is the intake structure of the Monticello Dam, which used a calcined diatomaceous clay as the pozzolan for the construction. So this structure is about 70 years old. Okay, we go back to 1940, when Thomas Stanton first discovered alkali silica reaction. And in his landmark paper on ASR, he also discovered that pozzolans could actually control ASR. So we've known this for 80 years, although you read some of the modern literature, it seems like we're just discovering it. But Stanton demonstrated that both a calcined shell and a Fresno pumicite could be used in his mortar bar test, which eventually became ASTM C227, to control ASR. And shown there as a comparison to ground quartz in the bottom left there, ground quartz being an inert material. So you can see that the pozzolans work, that their effect is beyond just mere dilution of the cement. The Davis Dam took advantage of pozzolans and actually specified pozzolans to control ASR. So back in 1950, engineers were using pozzolans in major structures to control ASR. And the work that was conducted by Gillian and Moran, published, they were the people who basically developed the idea of using Pyrex glass as a standard reactive aggregate in mortar bars, and demonstrating one of the specification requirements for the pozzolan used in the Davis Dam was that it could control ASR in the Pyrex mortar bar test. And they also had chemical requirements for the pozzolan there, which is fairly interesting. Minimum quantities of the silica, alumina, and iron, and a maximum quantity on both the calcium and the alkali content. Stanton was a pretty smart guy. 8 years later, he published work to show that pozzolans were also effective in controlling sulfate attack. And we look at this graph here. This is from his published work in 1948, published in the ACI journal. And you can see in blue there the line showing a very rapid deterioration of mortars containing straight Portland cement with a very high C3A content, whereas the mortars with 30% calcined shell perform much better with no deterioration occurring in sodium sulfate and reduced rate of deterioration in water bars, magnesium sulfate. So what happened next? Well, pozzolans around about 1940 discovered by work at the University of California in Berkeley that fly ash for residue from burning coal in a coal burning generating station, fly ash was indeed a pozzolan, and did many of the things, in fact, all of the things that natural pozzolans did. It could reduce the heat, it could control ASR, control sulfate attack, and it was indeed a viable alternative to natural pozzolans. And of course, any natural pozzolan requires some degree of processing, even if it's just digging it out of the ground, drying it, grinding it, whereas fly ash could be taken almost directly from the precipitators and used in concrete with very little processing. And the economics of this meant that fly ash slowly became the dominant pozzolan for the second half of the 20th century. The first major use of fly ash was in the repairs done to the Hoover Dam. It wasn't used in the main construction of the Hoover Dam. That was built a little bit too early for that, but it was used for some major repairs to one of the tunnel spillways. The Hungry Horse Dam, built around the 1950s, was really, I'm showing this photograph without any text here because it truly is a beautiful photograph showing the Hungry Horse Dam in Montana. This was built, say, the late 1940s. At the time it was completed, it was the third largest and second highest concrete dam in the world. It used over 100,000 tons of fly ash. And, excuse me, I'm trying to get rid of that. Minimize the window so I can see my screen myself. The fly ash was actually shipped all the way to Montana from Chicago, Illinois. Despite the huge cost of the shipping, it was still half the cost of Portland cement, and this resulted in what was then a considerable saving in the cost of cementing. Here are the mixes that were used. So in the mass concrete, up to 32% fly ash was used in the concrete. They did, if you look through some of the documentation on the use of fly ash in the structure, they did suffer a few air entraining problems, eventually traced to carbon in the fly ash, and they compensated for this by increasing the air entraining dose. I show these slides to my students because they complain about when they have to use 6-inch cylinders instead of 4-inch cylinders because of the increased weight. So I show them these slides to show some of the cylinders that were used back in the day with mass concrete structure. I mean, this was 6-inch aggregate, so you can't really use a 6-inch cylinder. Blanks published some information on this, showing the strength development, typical curves that you'll see in the literature throughout the years, showing that fly ash has a reduced strength at early age, but by the time you get out to about a year, even at 40% replacement, strength is equivalent to cement concrete. It's interesting, we go back to the papers from Berkeley and Davis's first paper on ASR in 1937. Davis discovered that this reduced strength of fly ash concrete at early age was something that really only occurred with our standard curing in the fog room. And if you actually exposed fly ash concrete to a temperature cycle that was similar to what it might experience in mass concrete, where it gets heated to temperatures of 100 degrees Fahrenheit and higher, then actually at 28 days, the strength of fly ash concrete could in fact be actually higher than Portland cement concrete. And some of us have utilized this in our careers. We've used temperature match curing when we use fly ash to demonstrate that the early strength of fly ash is not as low as we would expect from regular standard curing. Slag, of course, appeared in North America too, and there's another supplementary cementing material that came along, and also, I guess, partly displaced natural pozzolans. But even though slag has a much longer pedigree of use in concrete than fly ash, it took a little bit longer for it to really be utilized and taken advantage of in North America. And it wasn't really until the early 1980s that we started to see slag used as a separate addition to concrete. You can see in the last 5 years, from the slide at the bottom left there, in the last 5 years, there's been a very substantial increase in the use of slag in the United States. Silica fume didn't appear in North America till the 1980s. Its potential for use in concrete was known as early as the 1950s. It didn't get widely used in Scandinavia till the 70s, and then not really in North America till the 80s and beyond. One of the first uses, a major use in the US, was in the repairs to the Stilling Basin of this dam in Pennsylvania, where 86 MPa, 12,000 PSI concrete was specified for its high abrasion and erosion. Canada got off the mark quite quickly with silica fume, first field use being 1980, and the first blended silica fume cement appeared in Canada in 1982. 100 MPa concrete was a landmark, first used in 1984, and silica fume was finally included as an SCM in our Canadian standards as early as 1986, and it has since been used in some very major projects, including our Confederation Bridge, which is an 8-mile long bridge, at the time the longest bridge in the world when it was first constructed, with concrete strengths after a year reaching over 100 megapascals. So by the end of the 20th century, we pretty much demonstrated, with all the research that was conducted, demonstrated that SCMs really were invaluable. It took a long while to convince people and regulatory authorities, but I think by the end of the 20th century, most people were convinced that fly ash, slag, and silica fume and natural pozzolans, where they were still available, were good things for concrete, especially for concrete durability, and reducing permeability, increasing the resistance to chloride ion penetration, and also increasing resistance to things like sulfate attack, acid attack, ASR, and DEF. However, what we've also learned is that the performance of concrete is highly sensitive to the type and replacement level of the SCM used. The SCMs that are widely used in, if you look at fly ash, slag, silica fume, calcine clays like metakaolin, they're chemically very different from each other, and they are physically and mineralogically very different from each other. And therefore, careful consideration has to be given to how you use each one of these. And you can't interchange immediately and switch from one SCM to another. So it does require some careful engineering to take full advantage of all of these materials. So it's a happy story so far. So what happened? Well, recently there's been a great concern expressed worldwide about the future of fly ash. I'm just showing a couple of examples here from the Concrete Construction magazine. What is happening to fly ash? Well, about 5 years ago, we had a conference in the Anna Maria conference was focused. The title was "Living in a Post-Fly Ash World." We're of course not there yet, but we are slowly getting there. And we don't really need to discuss the reason why fly ash is disappearing. It's people don't like coal. People don't like burning coal. It's bad for the environment, although people don't accept that. It's generally considered that burning coal is bad for the environment. And And unfortunately, fly ash is a byproduct of burning coal. So fly ash is disappearing in Canada. Sorry, before I get there, I'll just show you some statistics, some data from the American Coal Ash Association here. The dark blue bars there show the amount of fly ash produced in the last 20 years, in 2000, 2018. You can see it's declined quite rapidly. In the last 10 years, between 2008 and 2018, there's a reduction of about 50% in the amount of fly ash produced.
Okay.
In Canada, this situation is perhaps even more dire. Our main coal fields are in Alberta, and the bulk of our generating stations are in Alberta. And I'm just showing you the situation in Alberta here. It is expected by the year 2023, which really isn't too far away now, that all of our coal burning power stations will actually convert to gas or dual fuel. So
will they take it? They'll be signed.
I'm sorry, I can hear somebody talking. I wonder if they don't mind muting. Thank you. So fly ash is going to disappear from Canada very, very quickly in the next few years. So this has brought about a renewed interest in the use of pozzolans, and we're seeing that in ACI. The Pozzolans Committee separated from the Fly Ash Committee in 2014 and is developing documents on pozzolans and also looking for test methods for natural pozzolans as well. In Europe, it's a similar situation because new supplementary cementing materials are appearing to replace things like fly ash. There are concerns about how we would test for the reactivity of these materials, and a number of test methods have been developed by this RILEM committee, two of which have now been adopted by ASTM. We actually now have two new test methods this year that are able to measure the chemical reactivity of SCMs directly rather than measuring it indirectly through things like the strength activity. So ASTM's activity included in 2018 the publication of a guide for evaluating alternative supplementary cementing materials. In 2020, these two RILEM tests for measuring reactivity, chemical reactivity by isothermal calorimetry in bound water. And also in 2020, we saw a specification for what's considered to be a new pozzolan in North America, and that's the ground glass use of pozzolan. Also recently as well, we've seen, because of the increased interest in pozzolans, we've seen the formation of a Natural Pozzolan Association and quite a substantial growth in the number of natural pozzolans actually being produced currently, and it's growing. I'm not going to read all those numbers on the side there. Read that. I'm sure you'll end up with a printed copy of these slides, a PDF or something. But there are new plants being granted permits, plants opening up, and the capacity for producing pozzolans, whether raw pozzolans such as volcanic ash and pumice or calcined pozzolans, the capacity is increasing quite rapidly. So we're going to see this sort of re-emergence of pozzolans that help fill the gap that's going to be made by the loss of fly ash. So how are we going to fill this gap? What are we going to do about this? Well, the things I'm going to talk about are harvested coal ash. There's still a lot of coal ash out there. Even if we stop burning coal tomorrow, there's still a lot of ash in landfills and lagoons that hasn't been used. The re-emergence of the natural pozzolans that we've known about for millennia, and the evaluation and adoption of new pozzolans, examples being ground glass. There's probably other materials out there. And also the development of innovative blended cements, an example being LC3. LC3 being basically limestone calcined clay cement, which is getting wide attention outside of North America. So if we look at this graph here, this is a graph dating back to 1966. And if we sort of integrate the area between that blue line, amount of fly ash produced, and the green line, the amount of fly ash used, I just did this as a quick calculation. Then in that 46-year period, there was about 1 billion tons of fly ash that have not been used, and have presumably gone either into lagoons or landfill sites. Now, I'm not saying all of this fly ash is usable, far from it, but a good portion of this fly ash we can expect to be usable concrete. There's been a lot of attention given to this. I'm just listing a bunch of references there if people are interested in following up on this. The work by McCarthy in Europe and work done here in the US as well, and by myself in Canada. There's been a lot of work showing that the preferred term for this has emerged to be harvested coal ash. Another word for it, of course, is reclaimed coal ash. This really is a viable proposition. The material that's in lagoons, so a lot of the material in lagoons and landfills is suitable for use with, in some cases, a minimum amount of processing. Some processing is obviously going to be required. I've deliberately used the term coal ash here rather than fly ash because very often fly ash is disposed of together with bottom ash. So they're both, you commingle them together in a disposal site, and then you have to consider it as coal ash. It's neither fly ash nor bottom ash, it's both. So hence the term coal ash. Myself and Doug Hooton just recently produced a report for the Canadian Standards Association on the use of harvested coal ash to demonstrate that it can be used. And in fact, in the Canadian Standards Association, we now have an item moving forward where harvested fly ash will be allowed for use in concrete from next year. It's not specifically disallowed by our Canadian standards, but it's going to be specifically allowed. What the data show almost invariably is that the material, once harvested, once it does require processing, such as removal of carbon, removal or crushing of coarse material, then the ash can be entirely suitable for use in concrete and behave as well, produce as good performance as fly ash that comes straight from precipitate. Bottom ash is much coarser than fly ash, so it can either be removed by particle size separation, or it can be crushed. The coal ash can be crushed because if you crush bottom ash, it's been demonstrated that crushed fine ground bottom ash is as reactive as fly ash, and can also improve chloride penetration and get ASR in the same way that fly ash does. So therefore, commingled coal ashes that contain fly ash and bottom ash, once ground, should be entirely suitable for use in concrete. We have a few caveats on this in our Canadian standards. And obviously, the landfill and lagoon sites have to be adequately logged and evaluated prior to use, and ensure that any deleterious materials are identified and moved. So moving on, so harvested fly ash, that will obviously will buy us some time when new fly ash, fresh virgin fly ash disappears. A recent development that we've seen is the use of ground glass as a pozzolan. There's been quite a lot of attention on this over the last 5 years. Ground glass, ground recycled glass is a very good pozzolanic material. Glassy materials are generally very good pozzolans. One of the problems is that the bulk of the ground glass, the bulk of the recycled glass available is from bottles or windows and what's known as soda lime glass. And this has a very high alkali content, and that raises the concern about alkali silica reactivity. But somewhere in the US produces about 20 million tons per annum of recycled glass. So it's obviously can't completely fill the gap left by fly ash, but it is a lot of material, which is at the moment it's landfilled, and of course it's not biodegradable. So that's a huge environmental problem. In Canada, we produce only about just under 1 billion tons. If you grind this material, and it needs to be ground to make it, it's still reactive if you don't grind it, but it's very slowly reactive and deleteriously reactive, as I'll explain in a minute. You need to grind it somewhere in the region of a D50 value of about 10 microns, and then it will become a highly effective pozzolan. Glass truly is an amorphous material. The concern, as I mentioned, is the alkali content. I'll come back to this in a minute. Soda lime glass has been identified as type GS glass by ASTM. E-glass, which has a low alkali content, is type GE glass. They would sit here on our ternary diagram here. So GS is quite close to silica fume on the ternary diagram, whereas GE contains more calcium. So the alkali is a concern. It's certainly a concern if you have a reactive aggregate in concrete. If you don't have a reactive aggregate in the concrete, then it shouldn't really be a concern. There is somewhat of and this is data of my own that show expansion of concrete prisms. You can see the red line there shows the type GS glass, which does reduce expansion compared to a high alkali control, but doesn't completely suppress it, whereas type GE glass does. Type GE glass being the low alkali glass. There is a somewhat of a paradox with glass and ASR. If we use glass as crushed glass as a sand, it can actually cause ASR because, of course, it's a reactive aggregate. It's a reactive material, but if we crush it finely, it behaves like a pozzolan. And can help suppress ASR. And I'm showing some of my own data here that shows expansion of concrete. The circles are, expansion of mortars containing Portland cement and Vicor glass as a reactive aggregate. And then the diamonds show the same mortar, but with 20% of the Portland cement replaced by ground Vicor glass. We've still got Vicor glass as the sand, but now what we're saying is the ground reactive aggregate is acting as a pozzolan and actually suppressing reaction with the coarse sand size glass. So if we grind a reactive material fine enough, it becomes a pozzolan and will suppress ASR. And we've seen the same thing in reverse. If we take a pozzolan that normally controls ASR and it agglomerates into larger particles like silica fume, then agglomerated silica fume no longer suppresses ASR, it behaves like a reactive aggregate. So we have to be careful of this when we're using silica fume. The particles are adequately dispersed. And for those of you who are interested, it has a recent paper just appeared in the last issue of Concrete International on the use of ground glass pozzolan for use in concrete, which does show that ground glass is an effective pozzolan, doing all the things you expect of a pozzolan, increasing long-term strength, increasing resistance to chloride ion penetration, increasing resistance to sulfate attack, and reducing ASR expansion. Type GE glass can do that on its own, whereas type GS glass, if you want to control ASR, it needs some help from another SCM, whether that's fly ash, slag, silica fume, or metakaolin, or a natural pozzolan. I'm not going to talk much about light and some calcined clay. It's just an example of some innovation. This is a material that only contains 50% clinker. The remainder is made up of calcined clay, limestone, and of course a gypsum that you would normally have in a Portland cement anyway. And this relies a lot on the normal pozzolanic reaction between the calcined clay and the clinker, or the calcium hydroxide that's released by the clinker, but also on the reaction between limestone and the alumina in calcined clay. It actually allows us to use limestone as a cementing material of that. It's reacting with the alumina in the clay. The clay deposits suitable for this in most parts of the world. If we look at North America, there the whole southeast has huge areas of clay that are suitable for calcining. Fortunately, India and China also have a large deposits of clay that are suitable as well. And these are obviously countries that should fly ash disappear from these countries, they leave a huge gap. Just demonstrating the very substantial impact these materials can have on things I'm showing here, just chloride ingress. Very much high, many magnitudes higher resistance to chloride ion penetration. Okay, so we have all these different types of SCMs. How do we evaluate them? You know, with fly ash and slag, let's take fly ash as the example. Pretty much we know how a fly ash is going to behave, but as soon as we talk about natural pozzolans, or pozzolans in general, we're talking about a huge range of materials that vary in terms of chemical and physical composition. So this is just a list of the various materials that exist. A really broad range of materials. And just stealing some tables here, which we're not going to spend any time on, but this just shows the variation in chemical composition of some pozzolans. This is from published information, and you can see the silica, alumina, iron, calcium content vary widely from one pozzolan to another. And the alkali content can be disturbingly high as 5, 6, 7%. Usually not an issue with a natural pozzolan because most of this alkali is tied up in crystalline phases and won't be available for ASR. But obviously we need test methods to determine whether that is the case or not. So this whole very, very broad range of materials really brings us to one of the issues here. We really are to take advantage of all the different materials that are available. We need test methods for evaluating the reactivity of these materials. There's a bunch of test methods out there. Most of them have problems in terms of very often it's poor reproducibility, or perhaps even more disturbing, it's just having very poor correlation with build performance. The tests that we have currently in ASTM and C311 and C618 for evaluating fly ash for strength activity index really is not very useful at all. It doesn't tell you anything about the performance of the pozzolan or fly ash in concrete. And it's incapable of screening inert materials. You can take crushed limestones and crushed quartz, which are non-reactive, and not reactive chemically in concrete, but they will pass the strength activity index in many cases. So I want to finish just sharing some work with you that we've been doing at UNB, evaluating a wide range of pozzolanic materials and some examples of inert fillers as well. And we've been looking at various different test methods, including the ASTM, the bound water test method. And our own, we developed a strength activity index based loosely on the old strength activity with lime index that used to be in ASTM. And I want to share some data from these tests with you and tests on concrete also. So our modified lime pozzolanic strength test is basically you produce a mortar where the binder is just a combination of calcium hydroxide and pozzolan. There is no cement, no Portland cement in these mortars. So the only strength that you'll get is from a reaction between the pozzolan and the lime. I don't have time to get into the details of the test. The idea of this test was to make it simple. The Ryland test, one of the Ryland tests requires access to a calorimeter, which most labs don't have. We wanted to develop a test where most current materials testing lab could run this test. You need to be able to make mortar cubes, and you need an oven and a cube busting machine, and pretty much you're good to go. So I'm showing some data here. I'm not sure if the pointer works here or not, but turn on the pen here. So the top graph here shows the 7-day strength of mortars. These are lime pozzolan mortars. You can see for the range of materials here, we're getting very different strengths between fly ash here and metakaolin here. But the test really is capable of distinguishing between inert materials and reactive materials. You have an inert material, you get no strength whatsoever. And generally, there's a good correlation with the bound water test from ASTM. Or this is the Rylam test that ASTM has now adopted. And this is a fairly simple test to do and only really requires access to an oven that can heat up to 350 degrees Celsius. So again, these test methods, both of these test methods are quite capable of determining the difference in performance between reactive and non-reactive materials. And what I'm doing here is comparing the 7-day strength in our pozzolan lime test with the bound water test. You can see there's an excellent correlation. Here are the non-reactive materials down here. And you can see the general correlation is very good. And we also get a very good correlation between the 7-day strength of the pozzolan lime mortars and the 91-day strength of concrete produced using the same materials. And this is important that the reactivity in the test is reflected by its performance in concrete. Although I have to say the concrete strength or mortar strength is probably not the best assessments of pozzolans. Pozzolans can produce great benefits to concrete without necessarily benefiting the strength. I think most of us who work with pozzolans will know you can reduce permeability without really increasing strength. And so you can get benefits without it necessarily being shown in terms of strength. These graphs here, this is the current ASTM strength activity index. It has almost no correlation or very poor correlation with the strength of concrete. So it's not able to distinguish between poorly performing and good performing pozzolanic materials. I'm going to skip over this slide and just show some correlations with some other materials. So again, a good correlation between the pozzolan lime strength and the charge passed in concrete. This is the rapid chloride permeability test, C1012, C1202. And again, inert materials give you no strength in the test. They increase the rapid chloride permeability, whereas materials that perform well in the pozzolan lime test also perform well in concrete in terms of reducing charge passed. And we get the same behavior if we look at chloride migration. So this is a real chloride test. We're actually measuring the penetration of chlorides into the concrete in this test. And again, we see our inert materials perform badly, both in concrete and in our pozzolan lime test, whereas materials that perform well so in both tests. Electrical resistivity provides a very good measure of the performance of a pozzolan. And if we did want an indirect measure of a pozzolan's ability to perform well in concrete, then concrete resistivity would in fact be a way to go. And again, this is showing a relationship between resistivity of mortar cubes made with cement pozzolan mixes and the 7-day strength again of our lime pozzolan test on the horizontal axis. If we look at ASR and sulfate attack, then having generally pozzolans are very good at controlling ASR and sulfate attack, but not always. That's not universally the case. Although we find that good pozzolans always reduce permeability and therefore always increase electrical resistivity, they don't always control ASR. We have, for instance, high alkali glasses may not control ASR, even though they behave very well otherwise as a pozzolan. And then we have high alumina pozzolans, which can have very good pozzolanic reactivity like metakaolin. But when they're used at relatively low replacement levels, like 10 or 15%, they're not going to help with sulfate attack because the alumina is contributing towards the amount of ettering that we perform. So we might not necessarily get an improvement in performance. So the conclusions from our study is a strength activity test for lime is a good way to move forward. The other tests, the Rylam tests, are also very useful. We do have now, today, we do have good test methods for evaluating pozzolans, whether they're new materials or existing materials. I think our increased use of these materials relies on us being able to properly evaluate them. So I realize I'm just on time here, and this is my final slide. So in conclusion, the fly ash has served the concrete industry admirably for 70 or 80 years now. It's going to leave a big gap for us, but there are alternatives to the use of freshly produced fly ash. And these include the things that I've talked about today. But this successful exploitation of this wider range of pozzolans and new emerging materials relies on us really being able to properly evaluate these materials rapidly and reliably for use as materials for concrete. Thank you.